Hi everybody, I wanted to put together a presentation on file systems, and in general the file system is the software component of the operating system that allows us to create, open, read, write, update, delete, manage files, as well as directories. And so a lot of times is this a directory system thing or is this a file system thing? Most operating systems will actually group both of those types of operations within the file system category itself. So when you think about the file system, think about just generally having the capability to manipulate files so we can store information from one user session to the next, as well as directories so we can then organize those files. And typically the file system kind of sat between the main operating system and hard disk space or floppy disk space, but today then it also sits between kind of a blank disk space, meaning the storage space can be magnetic, it could be flash-based, it could be cloud-based, and so our file system continues to expand with capabilities as we move out into things like the cloud. And so when we think about a file is just kind of a long, consecutive, or contiguous, meaning all the pieces are kind of bumped together, at least logically in our mind. They're not stored logically in consecutive sections on a disk or storage medium, but conceptually we view it as a long address space of bytes that we can apply meaning to, which can become data types. So our bytes can just be characters of data, or they could be character strings, or they could be floating point numbers. And so how we access those bytes give them the context. And so the contents of any file that is created is essentially defined by the individual or the program that's creating the file. And so at the end of the day, a file is stored as ones and zeros on the disk. And so it's a binary thing. But the structure of the file gives meaning to those bits. And so if it's just character-based data, then every 8 bits creates a character of data. And if it's numeric data, then depending on the data type, if it's integers, then 32 bits or 4 bytes would create a value. And if it was floating point, then maybe every 64 bits create a value. And so the context of the file and the information that's contained in the file is actually then defined by the program that's accessing it. So what do we know about a file? A file typically has a unique name. And that's where our directory structure comes in. We can have files on our disk with the same name, but normally not within the same directory. To the operating system, a file may have a unique identifier. And so it's not necessarily a number that we'll ever see, but it's something that the operating system is tracking. For operating systems that apply different types to files, and a lot do today. So we can have text files, we can have binary files, we can have Word documents, we have PDFs. We might have a type specifier. We know that our files reside on our storage medium, and so we need to know where. And so beyond just the start of the file, because it's not a requirement for most operating systems that the file reside in consecutive storage locations. That actually would make the file more difficult to manage. And so in most operating systems, they'll let them reside in what we'll refer to as blocks. And it might be a block of 512 bytes, it might be a block of 2,048 bytes, or 64K blocks. But they can just kind of reside in any block around the storage medium. And the operating system needs to keep track not only where they are, but kind of the order that they fall in. So you know, if the second block resides at this location, if their block resides way over here on the disk at a different location. And so the operating system, because it's got all these blocks of data to stay after, needs to know the file size. So it has a good feel of how many blocks is it taking. And then we'll have protection so we can secure our file and say who can have access to it and how can they access it. Some users can only read the file's contents, some users can update the file's contents, and even other users can delete the file's content. And then typically we'll have some date and time stamp attributes of maybe when the file was created, when it was last read, when it was last updated, and so on. So a lot of attributes that correspond to our file object. And so this screen, for example, just shows a lot of those attributes within Mac OS environment, but we can see the date the file was created, when it was last modified, its size in bytes, how much that's turning into in terms of blocks that are allocated on the disk, where it's located in the directory structure. In addition, behind the scenes, the operating system would track where it's located on disk. And so common file operations, again, we've talked about the fact that you need to be able to create one, read one, write one, find it on disk, and maybe not even just find the file, but find specific locations within the file. We typically refer to that as the seek operation. We need to be able to delete the file or truncate the file, open it so we can manipulate it in a program, and then when we're done manipulating it, close it. And so all these operations are typically built into the file system itself. And so to manage a file, we need to know, one, how to open it. And so we're going to open it for read operations, for write operations, for both. And once we've done that within our programs, we'll typically get a structure that's called a file pointer. And the file pointer tracks the location that was last read or written to within the file. And so our program can just kind of send information to the file pointer, and the operating system will, or the programming language will update the file pointer as we're reading from the file or writing from the file. So if we read the first 10 bytes of a file, the file pointer would be pointing at byte 11, so we can read it next. And if we're writing to a file, the file pointer gets updated each time we send information to the file to point to the next location where it's safe to write information. And so the operating system will keep track of what files we have open and how they're being accessed by a particular program. And so we talked about the fact that the file resides on a magnetic structure or even a flash-based structure, so some kind of storage medium. And typically those are slower than the computer's random access memory. And so we will do some caching, meaning we'll store pieces of the file kind of temporarily in normally a RAM-based cache. So if we know that we've read the first 10 bytes of the file, it's likely that we're going to read the next 10. So we can pre-read maybe some of those into memory so we don't have to continually go to the slower disk drive to read them. So caching becomes part of our file system. Now in a multi-user or multitasking operating system, it's not uncommon that two users could open the file at the same time, maybe even for different types of uses. And so that means we need to be able to allow shared access. We need to maybe be able to lock pieces of the file so one person's operation doesn't override another's, and so on. And so some of the synchronous tools that we've talked about before, such as locks and semaphores and things, come into play with the file system. Different file systems will provide different capabilities. And so here's some Java code, for example, that just basically sets up some variables that are saying how we're going to access the file. So it's not going to be exclusive. It is going to be shared. We are going to use shared and exclusive file locks. And so then we create a new random file. And so in this case, we're creating a file called file.txt. And we're opening it for read-write. That's what the RW stands for, operation. And once we've done that, then we can actually set a lock on the part of the file that we want and perform our operation. And then when we're done, we can remove the lock so somebody else can access it. So this is just an example of doing some file operations in Java. Behind the scenes, and this is still the remainder of the code, the operating system is actually implementing the locks. And so our programming instructions are telling the operating system what we want to do, but the actual locks and things are being controlled by the operating system, because another program, maybe different from this, can be trying to perform similar operations. And so common file types that we'll have is we've got program files that we can execute, and they typically have the exe, com, bin, file extension. We have compiled object code, source code, batch files, and so again, depending on the operating system that we're using, the file extensions may differ for executable files or for batch files. And then we may have word processing files stored in different formats. We know that we use PDFs. We know that we have multimedia files, that are movie files, audio files, sound files. And each one of these files with a different extension will normally have a unique file format that's meaningful only to programs that know how to open those particular files. And so that's why we have problems sometimes moving files from one operating system to another, just because we don't have the programs that know the structure of the file to be able to access them. And so again, we've talked a little bit about the file structure. It can be as simple as no structure, so we just have a bunch of bytes and bits sitting out there that we can access. And in the olden days, the MS-DOS days, that's typically our file format, and our programs would make sense of the corresponding bits and bytes. But again, the operating system and the program that's accessing the file makes sense or gives context to the file structure. We've talked about the file pointer that points to where we're currently manipulating a file. And so if we're doing sequential file access, then that implies that we're going to access byte 10, then byte 11, then byte 12 in a sequential format from the beginning of the file to the end. And so we have operations that we can perform that can rewind us back to the start of the file, or we can seek to a specific byte location in the file. And the best way to think about sequential file access is just, okay, maybe we're accessing a file that's stored on tape. Well, we then have to start at the front of the file and kind of read through the entire file in a sequential format. But we can have sequential file access operations for files that are on disk as well. And so, again, when we're doing sequential file access, it's kind of read the first one, read the second one, read the third one, or write the first one, write the second one, write the third one. So in order. Direct access, on the other hand, allows us to move to a specific location within the file. So I can say, I need to update byte 56, and I can jump right to that byte location and update it. So kind of are two different ways to approach file access. So sequential means we're going to process in order. Direct means we can kind of jump around to where we need to be. And again, some of our operations, reset or rewind, takes us to the start of the file. So you can see the current file pointer is at location, the current position is 0. We read a character, so we would then increment our current position or our file pointer by 1. We write a character, we increment our file pointer by 1. So we're doing everything in order. And so there are other types of file access operations depending on the operating system. And so IBM, older operating systems, for example, use something called ISAM, which is the Index Sequential Access Method. But it basically is kind of putting a layer on top of our common file operations. And so in this case, we're going to use indexes and things, but those indexes are really just doing either sequential file access or direct file access, but the operating systems making it easier for us to do so. And so we talked about the fact that we have directory structures, and so you can list the files in a directory. Conceptually, behind the scene, the operating system is doing kind of the same thing. And so once we open a file, we can then have the program that opened the file put context to the file structure. And so an index file might point to specific locations within a second file. So in this case, we've got a file that is an index file that keeps track of maybe usernames, Adams, Arthur, Asher. And so it's got the names in there, and then it points to where the corresponding record starts in the second file. And the reason that we would do this is if we don't have the index, then our option is to open the second file, read through every record to find the record for Smith. And that can be a time-consuming process. Our index file is much more concise. It's smaller, so we can read it faster, so we can open it, search for Smith, find Smith, and have it tell us that Smith starts at byte 1330 in the second file. Then we can open that file, go directly to Smith, and quickly retrieve it. And so we're paying a price for complexity, but we're improving speed because we can process the index file ideally a lot quicker than we could reading through the entire relative file in this case. Again, we talked about the fact that we have a directory which is a listing of files. In the simplest sense, a directory is just kind of a file that contains information about another list of files. And so a lot of times in the operating system, we actually treat a directory much like we would a file. So we can open a directory, read the list of files that are in a directory, and so on. So from a programming perspective, the operating system is just creating a capability for us to store information about files. And so to access a file, we go to the correct directory. We have to know the file's name, and so we can get a directory listing so we can find out the file's name. But a directory is just kind of a logical storage unit for files. So beneath all this, we have our disk or our flash memory or whatever our storage medium is. And so if we're talking about disk, we can actually partition that disk to take one physical disk and make it look like multiple logical disks. Probably up to 26 of them or something in most operating systems. So we have drive C, drive D, drive E, drive F, and so on, but they're all really on one hard drive. And so our file system is providing tools that allow us to do this. That's why disk partition operations are different on a Mac, and different on Linux, and different on Windows, because each has a different file system. Conceptually, the processes that they're performing are similar. So again, we can have partition A, which would normally be our drive C, partition B, and so we can make one disk appear as if it's mini, or we can make one disk appear like it's a really large disk because we didn't break it into multiple partitions. Typically, the nice thing about using partitions is that an errant operation, if I inadvertently format my disk or my partition goes bad, it normally doesn't impact the other partitions. But now if you think about this for a minute, we've got multiple partitions on a disk. The operating system has to know somehow where each partition begins and where each partition ends. And typically that's done by keeping track of a partition table that resides at a specific location on the disk. And so the operating system's managing all of this. And so we can have different file systems. And let's think about this for a minute, even in a Windows environment. And we have the file system that allows us to store information locally. But we're also starting to see more file systems that allow us to store information in the cloud and access them from our system as if they're local to our system. So lots of different types of file systems. Again, we've talked about things that can be performed by a directory. We can find a file, we can rename a file, we can move a file, we can delete a file, we can copy a file. And so these are all directory operations provided by the file system. And so ideally, because in a multi-user system, we may be performing a lot of file operations, we want to make sure that we can locate files quickly, update files quickly, cache files, and do things that, because disk drives are mechanical, they're going to be inherently slower than our computer's random access memory. So we want to make sure that all of our operations are optimized as much as we can. And so here's years ago when we first started, I think it was MS-DOS version 1 or PC-DOS version 1, we just kind of stored everything in one directory. And then possibly with version 2, we were suddenly able to create multiple directories and better organize our files. So you can imagine that if all your files were in one directory, it might become harder or even more time-consuming to find a specific file. And even for a program to open a file, it would have to read through all the files in the directory to find that specific file that you want to open before it could do the manipulation that you desire. And so then we came up with two-level directories, and it's kind of a recursive definition at this point in time because we could create directories within directories. And that became our tree-structured directory shown here. And that's pretty much what we're used to doing today. And we stopped calling them directories at some point in start referring to them most often as file folders. And so here's kind of an example of we're using the cd change directory command to specify the directory that we want. And so we want to move to the prog directory, which happens to reside in the mail subdirectory, which resides in the spell directory. So we've got multiple levels here. Once we've done that, then we want to display the contents using the type command of the file name list. And so our tree structure, we need to kind of, just as we start with a filing cabinet in our office, open the filing cabinet drawer, find a file folder within that filing cabinet. Similar concept with our tree structure directory. And so things that we can do in a tree structure directory is we can remove a file. We can make yet another level. We can change to that level. And so today we don't see the command line commands like rm for removing a file, or make dir for creating a directory, or change dir for moving to a directory. We just kind of click on folders within Windows or on the Mac, and all this kind of happens behind the scenes. So years ago we did all these operations from the command line. In addition, depending on the operating system, we can have shared directories. So we got a lot of directories on our disk, but we may have some that are specified as shared. And so, good morning, Ahmed. I'm just going through a presentation on file systems, which I'm creating a recording for. And so again, we can get fairly complex with the behind-the-scenes operations of the directories, so we can improve the performance. And so our goal is to make these operations as fast as we can. So if we can create additional pointers that point to specific commonly used directories, for example, then our operations become higher performance, and which improves the overall performance of the operating system and all programs that we run. Because most programs are going to perform file and directory operations. And so this is a kind of a look at a more intense pointer structured system. Why would we do this? Well, we do it to try to improve performance, but we're again trading complexity for performance. So a file system, before it gets started, the operating system performs an operation called a mount. And that's just basically the process of making the files in a particular area, particular partition, particular disk available for access. And so in a lot of operating systems, it's just transparent. We boot Windows and our disks are available. Behind the scenes, however, for each disk, the operating system is performing a mounting operation. And if we were using a system like Linux, for example, those operations are a lot of times specified by the system administrator as to what file systems, what partitions, what disk drives they want to mount and make available to users. And so we could say I've got a user's system out there, and so I want to make available, in this case, the SU disk and the Jane disk, and so anything that's in those file systems, make them available to users. Typically we have program files and we might want to load it. We've got data files that don't always need to be available. We can later mount the disk, so things don't have to get mounted at boot time. They just need to be mounted before the user can access them. We talked about the fact that we can do file sharing, and that each file may have different permission settings that controls which users or groups of users can get access to file. The operating system, via the file system, is controlling all these. And then again, we may have file systems that allow users to access content across a network. So we have remote file systems. And so they may be able to access files directly, or at least have the appearance or illusion that they are, via services that the file system is providing. And so we've seen different operating systems emerge. One of the recent terms that's gotten a lot of press is the term metadata. And metadata in its simplest form is just data about data. And so we might, for example, have data that's phone conversations. We'll just use the as an example. And for those phone conversations, maybe we've recorded them or maybe we haven't, but we have metadata that says how long was the conversation, so it's data about the data. Who was the phone call made from? Who was it made to? And so the phone call itself is data, but these other fields, such as the length of the call, the origin country of the call, those all become data about the data or metadata. The operating system doesn't really care. Metadata is kind of a concept that is program specific. So here's some operating system, file systems that are spoken about within the book, such as the Andrew file system, which allows remote sharing. The semantics is a term that describes meaning, so we're trying to put more meaning to the operations and the content and the data within a file. So we're making sense of the semantics. And we've talked about file protections that control what a person should be able to do. Some users may be able to read, some may be able to write, some may be able to execute the program, and so on, depending on the security level. The file system controlling all that. And so we can take a look at, in this case, some Linux securities, which come to us from the Unix world years ago, but we have an owner of the file, and it can typically do everything. So to represent that the owner can read, write, and execute, we give the owner all ones, so 3 bits can tell us quite a bit of information. People in the owner's group, in this case, can read or write the file, but they can't execute it. And the rest of the world, the public, can only execute it. And so we have an attribute bit, 6, 7, or 1, that controls what can somebody do with this file. So the operating system quickly can say, give me the access bit, look at it, see who the person is. Are they the owner of the file, or are they in the group, or are they from the world, and tell what kind of operations this person can perform on the file. In a similar Windows environment, we can right-click on our file and look at a property, and it will tell us that who is this person compared to the file, what access levels do they have, what do we want to allow them to do. And so we refer to the operations or the types of access that a user has to the file in the Windows environment as an ACL, or access control list. And that basically just defines down to the user, what can they do with this file? And the file system or operating system has to track that. And so again, this shows us a directory listing from Unix that tells us what can the owner do to intro.ps, what can the people do to the private folder, to the file program.c, for example. And so can they delete it, can they read it, can they write it? And so you see the different security settings that corresponds to each, for working from left to right, the owner, the group, and the public. Typically the public would have less access than the group, and the group would have less access than the owner. And so again, I wanted to put together this system, or this presentation. I will save the recording, and we'll move on to the next part, next components of the operating system. So thank you very much.